Hey. How's it going? Autonomous is here. Do you guys not have class this morning? Autonomous? I don't usually have class like before mine. Then why are you in my stream? Oh, okay. Really? That's lame. Yeah, we're gonna do some stoic. Tyler's pumped about doing stoic. Stoichiometry. Some good stuff. Did you guys see my sweet mug I got from the U? You shouldn't be scared, Drake. It's nothing to be afraid of. It's really just one more step on what we were talking about last time. Um, my weekend is good. Yeah. No, I got my master's degree, Tyler. That's the more impressive thing. My master's degree. Let's see. Isaac, my weekend was good. If you follow me on Insta, you would have seen me post a bunch. Um, so from Friday, Zach, yeah, we'll do a review from Friday when we do some of the problems. Yeah, well, when we get into this, it kind of goes together with what we were talking about on Friday. I mean, you can autonomous, so it's not gonna maybe help you very much, but it's something. I don't know. You have to do. Do you do balancing equations in bio? Maybe a little bit. It's so the units canceled, Cooper. The guiding principle between all this stuff is making the units cancel. So the biggest thing to remember is that you cannot change directly from grams into atoms or molecules. You have to use the mole as your central point. So that's kind of the idea, is that basically we're always converting everything into the mole. We'll do more practice today, and then we'll do, of course, Wednesday will be all homework practice, and so we'll get more practice, Cooper. So if you're still confused, hopefully we can start to make sense of it. Yeah, they're interesting to see some people talking about some of the biology teachers. There's some differing opinions. Claire, what are you doing in here? You're supposed to be with mom.
Mom, right
Do you want the straw?
I know.
Hey, there's mom. Go back with mom.
Come on. Come on.
Bye. I love you. Bye. Photoshop baby. Sorry, I'm reading the chat. Goodness. I don't understand what you're saying, Cooper. Babies confirmed Photoshop. No babies. Babies aren't real. Just like birds. They're government surveillance drones. He's probably downstairs watching TV, I think. My daughter's a troublemaker. She's the one that gets into stuff she's not supposed to get into. She climbs on counters. She puts her hands in toilets. She's the worst. Kids, man. They're ridiculous. Sneaks into streams. The ruiner as a kid. Trinity, that's a little much. She is definitely a rebel without a cause. I'll give you that, Cooper. Oh gosh. Good times. So just a little recap, right? Yeah, I don't know if she bites intentionally. Yeah, I think she has drawn on some things with crayon. She like ripped open a marker with her teeth the other day and got marker like all over her mouth. It was gross. Yeah, kids are weird. Pretty much, I don't know if it was like an orange marker. She might have gotten a blue one. Markers are non-toxic. Hey, that Twitch Prime sub. Thanks, Autonomous. And the Study Hall Gamer following me. Study Hall Gamer, that's a sweet name. Sub gang. All right. Yeah, I know, Cooper. I know. I'm working on it. It was my wife's birthday this weekend, so I was gonna do some stuff, but I just didn't get around to it. I'm gonna try to work on stuff tonight, and then maybe we'll have like some sub notifications and like donations, all the weird stuff, all the cool stuff for streaming. Nothing too much because of quarantine. We just went out. We got takeout sushi on Saturday, and then yesterday I made a cake. Here, I should show you guys the cake I made. And then I had like a steak dinner too that we made. Here, I'll send you a link of the cake. There you go. Here's my cake. Thanks, Cooper. Yeah, our school it's a public school. Autonomous. I think yours is like an all boys school, all boys Catholic school, isn't it? I was looking at it the other day. Yeah. Lemon zest, actually, Enya. It was lemon zest. We ate it / gave it away, so we gave some to some neighbors. All right, let's get started. We've wasted enough time. So we're going to talk about stoichiometry. Okay, that's our word for the day. Stoichiometry. I've been baking for a while. My wife, I'm a pretty good baker, so I always make stuff for holidays and things. Okay. Let's talk about stoichiometry. So the basis of stoichiometry really goes back to balancing equations. Right? Oh shoot, Matthew might get to it by the end. All right, so balancing equations is at the heart of all stoichiometry. So if we think about just a simple balanced equation, what does a balance equation actually mean? Let's take, for example, just some of the combustion of methane. So if we take methane, CH4 gas, and react it with oxygen gas to produce water and CO2, right? When we balance this equation, right? One carbon, 4 hydrogens, 2 hydrogens, we put a 2 here, right? 2 oxygens, 2 because it multiplies through, and then another 2, that makes 4 total, so we need a 2 there, okay? So when we balance it, yeah, so Cooper's basically saying we get the same number of elements on both sides. But what does it actually mean? Like physically, if I burn natural gas in oxygen, what's happening at an atomic level, from an atomic standpoint? When I say that one of these reacts with 2 of those, what does that even mean? Okay, atoms are rearranged. Good. Good. I like those ideas. Isaac's cheating because he's an AP and he knows something about moles. All right. So yeah, so autonomous is kind of along the right lines. It's not necessarily accelerate, but they collide into each other, right? It's an actual collision, and then that results in temperature and moving faster and energy and all that. But what we can really think about is we can think about, if we kind of drew just a little cartoon to represent this. Right? All right, so our methane, okay, reacts with our oxygen. So these 3 particles collide with each other, and then they rearrange. And so the idea is that for every one of these molecules, right, this carbon-hydrogen group, we need 2 oxygen molecules to combine. So we can actually rephrase this chemical equation, and we could say that 1 molecule of CH4 reacts with 2 molecules of O2 to make 2 molecules of water and 1 molecule of CO2. Okay. I tried to draw the hydrogen smallish. They should probably be a little bit smaller. You're right. Not drawn to scale. All right, so we have 1 molecule of methane plus 2 molecules of oxygen, making 2 molecules of water and 1 molecule of CO2. Now, do we have the ability to do reactions with individual molecules? No, you're good, Study Hall. Can we, so there are some researchers that do reactions with individual molecules, but for the most part, anytime you do a reaction, it's going to be with billions and billions of molecules. Okay, so can we? What's we learned about this on Friday? What's a convenient measurement of molecules? Like a count. Sadie says it, a mole. So when we say this, when we say a molecule of CH4 reacts with 2 molecules of O2 to make 2 molecules of water and 1 molecule of CO2, well, we could scale it up and we could say that, for every 1 mole of methane, we would need 2 moles of oxygen. And that produces 2 moles of water and 1 mole of CO2. And with that, we gain the ability to predict how much of something is produced. Before we did that, I wanted to reemphasize this idea of the law of conservation of mass first, right? So let's say that, for example, we had 1 mole of CH4 and 2 moles of O2, producing 2 moles of H2O and 1 mole of CO2. How much does 1 mole of CH4 weigh? What's the mass of 1 mole of CH4? To do that, we of course have to look at our periodic table. So we pull up a periodic table. We find hydrogen up in the top left. It has a mass of essentially 1.0 gram per mole. Maybe Drake, I might add a channel to the Discord for just random chatter. I'll do that this afternoon. I'll make a Discord channel. You guys can just put whatever you want. I'll moderate it, of course, but we'll do something. We'll do something. All right. Anyway, so hydrogen has a mass of 1 gram per mole. Carbon over here, right, has a mass of 12 grams per mole, 12.0 grams per mole. And so if we look at CH4, right, that's 12 plus 1 times 4, which is essentially 16 grams. Right? So 1 mole of CH4 would weigh 16 grams. Yeah, don't forget, Zach. Don't forget to 4 carbons, right? Or sorry, 4 hydrogens. Okay. Then we look at oxygen. Okay. So O2. So if we go to oxygen, so oxygen has a mass of 15.99999, right? Essentially 16. So we would say that O2, which is 2 oxygens together, yeah, Zach's got it, is going to be 32. Okay. So, but this is the key here. We've got 2 moles of O2. And so because we have 2 moles of O2, that gives us 64 grams per mole. Right? Because, well, it's not 64 grams. It's 32 grams per mole, but we have 2 moles. Hey, Octacore Bear, man. Thanks for the 500-bit cheer. That's awesome. Appreciate it. All right. So 64 grams of O2, because, again, there's 2 of the 32, which makes 64. We're going to get into the math of this a little bit later, so don't stress about that. Okay. Now, real quick, before we move on, he wanted to be that top bit donator. All right, so we get, what is this? That's 80 grams. Okay. Why does 1 mole equal 1 molecule? I'm confused. Okay, so let me. I didn't do a great job of pointing that out. And yeah, let me really reemphasize that. So what we're saying here is we're saying that we can't actually do this reaction in terms of molecules. But what we can do is if we scale it up, and if we take this idea and we times it by Avogadro's number. So if we do this reaction Avogadro's number of times, then instead of saying 1 molecule reacts with 2 molecules, we can say 1 mole reacts with 2 moles. It's a ratio, right? It's the idea that, if you can buy, 3 donut holes for every donut, you could buy 3 dozen donut holes for every dozen donuts. Does that make sense? It's the idea that you can scale it up. The coefficients give us our ratio, and we can scale it up to moles, which are convenient because we can physically measure a mole. We can't easily measure a molecule. Yeah. So 2 moles and 1 mole on the products, right? So let's go back to the weights. Let's look at this weights idea. So water, right? How much would a mole of water weigh? Again, periodic table, we said hydrogen weighed 1 and oxygen weighed 16. So if we have H2O, that should be 18, right? And because there's 2 of them, that makes 36. Yeah, don't forget that there's 2 hydrogens, Drake. Yeah, you got it. You caught yourself. Yeah. Yeah, 36. All right, and then what about the CO2? So we said carbon was 12, oxygen was 16, right? So if carbon is 12 and oxygen is 16, we take 16 times 2, which is 32, plus our 12 gives us 44. Now, what do you notice about 36 and 44? Sorry, you can't say STFU. It adds up to 80. Yeah, Tyler caught himself. 80. So you'll notice, right, the left side equals the right side. And so when we say law of conservation of mass, right, we actually can relate that back to our gram per mole idea. And so mass is conserved, right? When we look at the individual number of atoms, we can see that the individual number of atoms are conserved. But when we scale it up to grams and moles, we also see that our total number of grams are conserved, okay? It's almost as if it conserves mass. I know. Big brain, big brain. All right, we're all having a. I know, guys. I know. I'm speaking some big truth. All right, so the amount of grams has to be equal on both sides. Yeah, and it will. So the reason I'm emphasizing this, Hunter, is that if you have a balanced equation, this math will always work out. And so I just kind of wanted to emphasize that you don't have to do this every time. You don't have to add up these and multiply through. We're just doing this as kind of an example. But it does, and it will add up every time if your equation is properly balanced. So let's show how we would actually use this in kind of a practical sense, right? Let's go to the actual stoichiometry. So we'll call this, actually we'll just call it theoretical yield. Yeah, this is the basis of stoichiometry, Ellie. What we're going to do next is kind of more so stoichiometry. Stoichiometry is math autonomous. That's what stoichiometry is chemistry math. It's math with a balanced chemical equation. It's the foundation, Ellie. We'll get there. Okay, so let's talk about, let's do a theoretical. So let's use the equation we were just using. No, let's do a new equation. What do you mean, Lauren? The math on the periodic table? The mass, sorry. It's the bottom number from the periodic table. All right, let's do another equation. Let's do what's a good one? Let's see if we can refine some iron, right? So if we take hematite, which is Fe, one form of it's Fe2O3, and you react it with hydrogen gas, you can make solid iron and water as a gas. You kind of have to do it at a high temperature. Sorry, I should do gas, solid, right? Okay. All right, you guys are just doing random stuff in the chat, nothing important. All right, so first thing we need to do is we need to balance the equation. This equation is not terrible to balance. 2 irons here, so we need 2 irons here. 3 oxygens, so we need 3 waters. Then we have 6 hydrogens, and so a 3 would make 6 hydrogens. Okay, so again, that's just balancing equations. So I hope you guys can balance. We've done enough balancing. I'm not going to kind of go through balancing in more detail than that. If you need more help on balancing, there's tons of balancing reviews and things that you can find. So the question, this is stoichiometry, is how much iron we'll say in moles can be produced from, I don't know, 15 15 grams of hematite, which is Fe2O3. Right? So using this reaction above, I want to know how much iron can we produce if we use 15 grams of hematite, right? So if we take a chunk of hematite, this iron ore, and we react it with hydrogen, and we take a 15-gram chunk, and we fully react that 15-gram chunk, I want to know, well, how much iron do I get out of the process, right? And so the setup is just like the setup of all the problems that we've been doing. It's a factor label conversion idea. How much iron in moles? So that's the question. So our answer is going to be some amount of moles of iron, right? So how many moles of iron is equal to our starting point, 15 grams of hematite. Okay. So now our challenge, does the reaction come from matter? Can we just use the periodic table? Yeah, and I'm going to get to why that matters in a second, Enya. You'll see. Let me work through this one with you guys, and then I'll let you I'll set you loose to maybe do one or two on your own eventually. So I want to kind of walk through this first. So the first thing we notice is we've got grams of Fe2O3. So our first conversion, no matter what it is, has to cancel that unit. And so down here we need grams of Fe2O3. Now, what do we know? What's the only thing we know about grams of Fe2O3 that we can use as a conversion? The only thing we know is the periodic table. Right? So we go to the periodic table. Iron, right here in the middle, iron, right, has a mass of 55.8. For our purposes, you can get away with using one place past the decimal. The other ones we did in the last example all had zeros, so we didn't write them, but you would always want to go one place past the decimal, at least for our class. So we're going to use 55.8 for iron, and then oxygen is 16. And so we need to do this math here, to find the mass, it's 55.8 times 2 plus 16.0 times 3, right? So that's going to give us our mass of iron. Drake's saying it's, hey, so Drake's telling us it's 155.6. Let me double check him. I trust him, but let's double check him. Wait a minute. Drake, I'm getting 159.6. What? Why is that sexual? Happen? Don't call people fools. I don't understand why happen is a whatever. Automod's weird. All right, so 159.6. Now remember, this is the number of grams of iron in every 1 mole, of hematite, in every 1 mole of this Fe2O3. Now, this is where it's a little weird, because here we have moles of Fe2O3, but I want just moles of iron. And so what we do, in order to change one compound into another compound, this is stoichiometry. This is where what we do is we use the equation. So what we do is we look at the coefficients in our equation. We see that the Fe2O3 has an understood coefficient of 1, and the iron has an understood coefficient of 2. What that means is, what we just did in our last example is we can now say that 1 mole of Fe2O3 will produce 2 moles of iron. Right? And then at that point, we're done. Okay, so look at how the units cancel. Grams of Fe2O3 cancel with grams of Fe2O3. Moles of Fe2O3 cancel with moles of Fe2O3, right? And so our units cancel. We get left with moles of iron, which is what we were trying to find. How does it make 2 moles? Again, we use the coefficients. 1 mole of Fe2O3 makes 2 moles of iron. So if we trust that we've properly balanced the equation, that's what our equation is telling us. That's what our coefficients are telling us. So again, this is from the P table, periodic table. And these are our coefficients. So it would also make 3 moles of water, Tyler. Yeah, it would also make 3 moles of water. Or we could say, I guess, 3 moles of oxygen as well. But I would be more inclined to say 3 moles of water according to the equation. So 5 out of 399, let's just do that as a decimal. 15 times 2 divided by 159.6 gives me 0.1879. So I'll just say 0.188. So apparently we can get 0.188 moles of iron. No, you're good, Enya. So again, remember, you multiply the top, divide the bottom. Okay, let's do some more examples. Yeah. Hold me up, Zach. What's your question? This final answer, 0.188. I took 15 times 1 divided by 159.6 times 2 divided by 1, and I got that as my answer. So you multiply the top, divide the bottom. Yep, just like we've been doing for the past 3 or 4 days. Yep. It's just weird because we're doing moles and grams and equations and chemistry with it rather than kind of stuff that's more trick. All right, let's do another one. Number 2. Another one. Let's see. I'm trying to think what I want to do. What's a good equation? Sure. Phosphoric acid is formed by the reaction of water. Water? There's a couple, Zach, on the worksheet. I can't remember how many. Probably like 5 or 6. No, that one's so the problem with that one, Drake. That one's just a 1-to-1 to 1-to-1 ratio. I want to get some coefficients. So let's do the reaction of water with P4O10 to make phosphoric acid. That's just a simple single replacement reaction. All right, so let's see. We've got 4 phosphoruses. So I'm going to start with a 4 here. That makes 12 of these, so we need a 6. Double check the waters. 6 plus 10 makes 16. 4 times 4 makes 16. Okay, so water can react with P4O10 to make phosphoric acid. So let's see. Let's say we're running an industry and we want to make, I don't know, 100 grams of phosphoric acid. So the question is, how many grams of water are needed to make 100 grams of phosphoric acid. Okay. No, and just a lot of reactions that I know randomly and have memorized have water in them. That's just kind of me. So it's not on purpose. It's just the ones that are coming to mind. So all the coefficients of phosphoric acid will be its mole numbers. So yeah, so we can interpret this equation as 6 moles of water reacts with 1 mole of P4O10 to make 4 moles of phosphoric acid. It's just water is a really common reactant, Zach. It's really it's a really common thing that we use. All right. I want to give you guys a minute or two. See if you can set this up and see how far you can get. I want you to get stuck on the problem so that I can help you through it. Okay. So if you have paper, grab some paper out, work through it. See where you get stuck, so that way you can kind of anticipate the questions you'll have on the homework and things like that. So I'm going to give you like 2 minutes. 2 minutes. I should have a 2-minute timer, but. See what you can get. Grab a piece of paper. Don't be lazy. Grab a pen. See where you can get on it. I'm going to drink out of my sweet University of Utah mug. Thousands of dollars in tuition, and I get a mug. and a degree, but... it's a water-based beverage. No, it's just like a. I don't remember what I added. I think I added some Mio energy. Because I stopped drinking energy drinks, so I still need caffeine from something. Yeah, but coffee you have to like brew, and then you have to let it cool down, and you drink it too hot and you spill it on yourself in first period, and then everybody laughs at you and your shirt's stained. It's rough. I would say watch yours, Ellie, but I'm pretty sure it's still burnt from your coffee. All right, let's see how far you guys got. Let's see where we got. I'll go slow through it, right? So the question, how many grams of water? So blank grams of water equals. Zach says 108. We'll see. So how many grams of water? Now, how many grams of water for what? How many grams of water are needed to make 100 grams of phosphoric acid? Okay, so if you got the setup, that's good. That's important. Okay. All right, so how many grams of water? 100 grams of phosphoric acid. So what we need to do is we need to figure out the mass of phosphoric acid. We need to figure out how many grams are in a mole of H3PO4. Now, I know that hydrogen weighs 1 and oxygen weighs 16, but I don't know phosphorus, so I need to look at my periodic table to double check phosphorus. So phosphorus is in the middle. It's 30.97, which we can round up to just be 31. Okay. So that means we need 3 times 1 plus 31 plus 16 times 4. So whatever that mass is, that should give us the grams. So let's see. So I get 98. Hey, good, 98. All right, so some people got that 98. So there's 98 grams of phosphoric acid in every 1 mole of phosphoric acid. Okay, so that was our weight from the periodic table. So, Zach, so that's a good question. So why do we have to put it in moles? The reason why we have to put it in moles is so we can use the equation. The equation relates phosphoric acid to water, okay? But it's not grams, right? Our equation doesn't relate things in terms of grams. Our equation relates things in terms of atoms and molecules, which we can use moles to represent. So we can't use grams, which is why we have to change into moles, right? And so then this is where we use our coefficients. We say 4 moles of H3PO4 comes from 6 moles of water. Now we need grams of water, so we have to do one more step where we convert moles of water back into grams of water. Right? Good job, Cooper. 1 mole of water, and we said this from earlier, but it was 18 grams. Never mind, you forgot the last step. So Cooper probably found moles, but the problem asked for grams. So we have to do this last step where we say 1 mole of water is 18 grams of water. Okay. So notice the units again, how they cancel. Grams of phosphoric acid cancels with grams of phosphoric acid. Moles of phosphoric acid cancels with moles of phosphoric acid. Moles of water cancels with moles of water. And we get left with grams of water, which is what we were trying to find in the first place. Again, these two conversions are from the periodic table, and this conversion is from my balanced equation. All right? Okay. So I'm going to multiply through 100 divided by 98. All right, I can show you guys. 100 divided by 98 times 6 divided by 4 times 18, I get 27.6. I am but an idiot fool. Yeah, 27.55, 27.6. So we need about 30 grams of water to make 100 grams of phosphoric acid. Now, I guess this is something called, gosh, why is it blocking it again? Oh, it's because you changed it to fools. All right. So, again, now, if we used 27.6 grams of water, right, would we get 100 grams of phosphoric acid? If we did this in the real world. Why not, Cooper? Why would we? Why wouldn't we? That's what the math says. What are we? Yeah. So we're leaving off P4O10. Okay. So there's an innate assumption here that's assuming we have enough P4O10, right? So technically, I should say assume excess, right? Meaning we have more than we need, excess, extra, or enough, excess P4O10. So often you'll see like this reacting with excess something else, okay? Yeah, so we do need to include this idea of P410. But even if we used enough P4010, would this work out to be perfect? Crimson, I don't actually know the equilibrium constant for this reaction. I'd have to look it up. I mean, everything has some sort of an equilibrium constant. I don't think it's... maybe. I don't know. Okay. The other issue is that we could potentially have some side reactions. We could get some decomposition of some products. There's all kinds of other things that could happen that could drive down this yield. So when we do this math, it's not always going to work out perfectly in the real world. We're making some assumptions, and then we're going to lose some things. So yeah, Lauren, he spells it Z-A-C-K. He's a Zach with a K. Okay, let's do. You guys are like so many side conversations. Let's do another example, and that'll be kind of our last example. What should we do for this third one? I'm trying to make up another equation. Let's see. What's another good reaction? We just do something simple. Yeah, let's do something simple. Let's take. Let's just do like a simple synthesis reaction. So we'll do like calcium. Do I want to do that? That's too simple. Let's do like nickel. No, let's do. Here's a periodic table. Sure, let's just do this. So let's take chromium solid plus oxygen, making Cr2O3. So we're just going to oxidize some chromium. So I'll have two simple questions. So first question, all right. Okay. I don't know. All you needed was the first part of the problem. All right. So let's take chromium plus oxygen, so Cr plus O2, solid and gas, making Cr2O3 solid. Now, I have not balanced that equation, and I didn't balance intentionally. I wanted you guys to balance it. So the first question asks, how many moles of Cr2O3 can be formed from 1.8 moles of oxygen? Then the second problem asks, how many grams of chromium would be needed for this reaction that I described in part A? Okay. So what's our first step? What do we need to do first? Yeah, Tyler's got it. We got to balance the equation. Okay, 2 chromiums. Oh, this is going to be annoying with the oxygens. So I have a 2 here and a 3 here, so I need to get them both to 6, right? And then that gives me a 4. So 4 chromiums, 6 oxygens, 6 oxygens. All right, so our first question, blank moles of Cr2O3 from 1.8 moles of O2. Okay, so we got to be careful. They already gave us moles, and so we don't have to convert into grams because they're already in moles. So we just use the coefficients from the equation. 3 moles of oxygen produces 2 moles of Cr2O3. And so we get 1.2. Okay, so this one was really simple because this was already in moles and I wanted our answer in moles. We don't have to do any periodic table conversions. We don't have to convert from grams. We don't have to do any of that stuff. We just have to use the equation and say, oh, it's 3 to 2. Okay. Now, part B says, how many grams of chromium would be needed for the above reaction? So we want to know how many grams of chromium. So blank grams of chromium are equal to. Now, what should we use as our starting point? The problem just says how many grams for the above reaction. So Tyler says 1.2 moles, but you got to make sure you specify. If you use 1.2, it's not 1.2 moles of anything. It's 1.2 moles of Cr2O3. Okay. And the reason why that's important is because we have to know which coefficient to look at. So we know that 2 moles of Cr2O3 comes from 4 moles of chromium. And then because we're trying to find grams of chromium, we need to change moles of chromium into grams of chromium. We need to look at the periodic table. Chromium is 51.996, or essentially 52.0. Now I have moles here, so I know 1 mole of chromium is 52 grams of chromium. So don't forget that when you do the grams to moles on the periodic table, moles always gets the 1 and the grams gets the weight. Is one of those an I and one of those a 1, Drake? So I get 125. Technically 124.8, but oh, it's an I and an L. That's what it is. Yeah, so 124.8, 125. Good job, Tyler. All right. So this is essentially what your worksheet is. I'll get the Canvas submission up, if not this afternoon, maybe tomorrow morning. It just needs to be within 5%, Hunter. So I would at least use 3 digits, right? So you see how up here I used 27.6. Here I used 125. This is technically 1.20. But I would use 3 numbers so you don't get it wrong. No, you're good. This is it for today. Oh, Zach's close to redeeming his bits. I would bet. That's my bet. All right. I think that's it. A reminder: the worksheet can be found. The worksheet can be found if we look on Canvas under modules. So let's see if I pretend I'm a student. Yeah, 3 numbers, Tyler. That's a good way to think about it. Modules. Nice. Yeah, he lied to you. What a jerk. So remember, we have a stoichiometry worksheet. It's under the, it's right here. So these first couple of problems are just conversions from grams to moles, like we were talking about on Friday, and also we talked about today. And then these last 1, 2, 3, 4, 5, 6 problems are all of what we were just doing, right? So it's just using the equation. So Weaver's class, it's on the homepage with the chapter 2 link. I'll get the submission ability up. I don't care if you say thick. So yeah. So make sure to get this. Make sure to start it. We'll be going through any questions you might have on Wednesday. I'll probably work through a couple of the problems. Maybe a couple of the more challenging ones. But then it's due on Thursday. So I'll have the submission assignment up either tonight or tomorrow. Yeah. Now it works, Drake. You're good. All right. Okay, that's it for today. Have a good rest of the day and enjoy your Monday. We only have 2 weeks left in terms of like content, new material stuff. So thanks, Naya. Thanks for tuning in. Have a great rest of the day. George Tech guy? No way.